combined 7.3 and 7.4. So let's start talking about sampling distributions and proportions. Let's take Reese's Pieces, for example. They come in 3 colors, orange, brown, and yellow. If you repeatedly take random samples, like, in other words, you look at different bags, like a whole bunch of them, like 100,000 bags of candy, do you expect the proportion of orange to be the same every time? Or do you expect to see variances between each bag or each sample? If these sample proportions show variability, how much will they vary? Most importantly, will the sample proportions display any predictable pattern? The same issue arises in more important contexts. For example, when a polling organization asks a random sample of people whom they intend to vote for, how much variability can be expected in a sample proportion from one population, one area, from another? If I keep sampling, will I eventually be able to predict the winner? If a predictable pattern really does emerge, then the pattern could enable you to anticipate how close the sample results are likely to be to the proportion for the actual population. In other words, the percentage of a certain color candy would be for the entire production of Reese's Pieces, or who would win that election. So we're going to be looking at proportions with sampling distribution first, because it makes more sense, I think, in your brain. So remember that population is the entire collection, samples are subset, parameter is the numerical measurement of the population, and statistic is the numerical measurement of the sample. Sampling variability just means that every sample you take can vary from here to here. Okay, so remember that population parameters, proportion is P, mean is mu, standard deviation is sigma. For statistics, P hat represents the population, the sample proportion. X bar represents the sample mean, and S represents the sample standard deviation. So we're going to be looking at the population proportion or percentage. So in each case, we can find the statistic. That's easy. The proportion of like orange candies out of the total, that's easy to find. And as we gain more and more samples, we can see theoretically what, if we take the mean of all the samples, that's going to get us close to the mean of the true population. Same with standard deviation. And that's called the central limit theorem. The central limit theorem says that we take a random sample from a large population, then we can predict 3 things about the sampling distribution. In other words, if we took all of the samples and combined them, the shape of the distribution would be approximately normal. The center, the mean, would equal the mean for the population. So that would mean that if we took the mean, the average of all the p hats, it would approach p, right? The standard deviation, there's a little formula for the standard deviation that will be, it's pretty easy. It's p times 1 minus p divided by n, divided by the sample sizes. Now, this normal approximation becomes more and more accurate as the sample size increases, and that makes sense. And it's generally considered to be valid as long as your sample size times your proportion is greater than or equal to 10. And your sample size times the opposite, your I'm going to lose the word for it. The opposite, Anyway, the opposite of that proportion is greater than or equal to 10. So the conditions for this to work, and this holds true for any sampling distribution. The samples need to be random. They need to be independent. Your sampling of one product doesn't need to affect another product. And it has to be large enough. You have to have a large enough sample. Like asking 5 or 10 people is not going to be big enough. So just a quick what if, just so we could talk about. So what if our sample size was 500? And we said that the proportion of people who vote yes, of voting yes, is 20%. In other words, P is 0.20. That would mean the mean of all these distributions would be 0.20, right? If I average them all up, the percentage of people voting yes should be 20%. If I grabbed a whole bunch of samples of size 500, oh yeah, they'd be close to that. The standard deviation, the formula says I'm going to take the p-value, 0.20, times the opposite, 1 minus that. So that'd be the 80% that are going to vote no, divided by the population size. Pretty easy formula. So clear second square root. And you can even do a fraction here if you want. 0.2 times 0.8 divided by 500 gives me a standard deviation of 0.018. Now, I forgot to do something. I forgot to check my sample size to see if this was even a good idea to say that the mean is 0.20 or the standard deviation is 0.018. Is 500 a big enough sample size? Well, let's check. So N times P, in other words, 0.20 times 500, 20% of 500, 0.2 times 500 is 100. Is that greater than or equal to 10? Well, yeah. We also need to check N times the rest of the population. So that'd be 0.80 times 500. Well, that's going to be the rest of the population. That's 400. That's definitely greater than or equal to 10. So yes, we can assume that the mean is 0.20 and that the standard deviation is 0.018, as long as those conditions are met. The concept of sampling distributions can be very difficult to grasp. Just remember that when we're talking about the sampling distribution, we're talking about taking all of the samples. For example, in the Reese's, I'm not just looking at one bag, I'm looking at a whole bunch of bags of candy, and I'm taking the average of the proportions. The mean is the average of the means, the average of the proportions. And we need to be careful to remember that a parameter goes with population and statistic goes with sample. So the central limit theorem talks about 3 things. It's going to talk about the shape, that it's normal. The center is the mean, and the spread is standard deviation. So the first thing you're always going to do is make sure that we verify our conditions. Make sure we have a large sample. The normal shape depends on this condition. So you have to make sure the sample's large enough before you can do anything. And I should have started off that other one with that first, that we verified that. So in each problem from now on, let's verify our conditions first. Now try not to confuse the sample size with the number of samples. Like on that one, we had a sample size of 500, but I could take 1,000 samples of that size. The main thing we're looking at here is the sample size. So first off, if we have a sample size of 400 and our proportion is 0.5, we want to check our sample size. So N times P would be 400 times 0.5. That's an easy one. That's 200. That's bigger than 10. What about N times the opposite of P? That would be 1 minus 0.5. Well, that's still 200. That's good. If it meets those two conditions, then we can assume that it's normal and that the mean is our p-value, and our standard deviation is found by this formula. P times the opposite of P, or the complement of P. I finally remembered the word for it, complement. So I'll be taking 0.5 times the opposite, which would be 0.5, over 400. .5 times 0.5 divided by 400. You don't actually have to put it in the fraction. This works just as well, 0.025. What about a population size of 1,600? What do we think? I kind of have a sneaking suspicion this is going to be mighty okay. 800 of them voted yes. That means 800 voted no. This is going to be a good sample size. The mean is going to be whatever that p-value is. And the standard deviation is found so I'm really just changing that last one. So I'm going to go up and copy that and change that to 1,600, 0.0125. In a random sample of 200 drivers, 50 individuals say they never wear a seatbelt when driving. Suppose the population proportion of people, is 30. So P is 0.30. Give a numerical value of the sample proportion. Well, this sample said that 50 out of the 200 said they don't wear a seatbelt. So that would be 0.25. Then it says calculate the standard deviation. Well, I can't do that unless I check my conditions. Check conditions. So N times the P from the population, N times P, that would be 200 times 0.30, which is 60. That's bigger than 10. N times 1 minus P is 200 times 0.70, which would definitely be bigger. That's 140. So the conditions are checked. That means I can find the standard deviation of the population. That is going to be using the population proportion. So 0.30 times 1 minus that, that'd be 0.70, divided by 200. .032. In a different survey, we had a survey of 400 drivers. 100 people say they never wear a seatbelt when driving. Give the numerical values for p hat and the standard deviation for p. Again, is 400 going to be good? If 200 was good, I think 400 is going to be good. So if we checked it, it would be fine. P hat is the sample proportion. That's just taking that 100 out of the 400 drivers. The standard deviation, we actually use the population standard deviation, but divided by the new n value. Okay. The Centers for Disease Control and Prevention reported that 20.9% of American adults smoked regularly in the year 2004. Treat this as a parameter value for the current population. P is 0.209. Our sample size is 100. So we need to check to make sure we meet our conditions, right? So check our conditions. N times P. So 100 times 0.209 would be 20.9. That's good. N times 1 minus P would be 100 times, 1 minus 0.209 is 0.791. That'd be 79.1. That's definitely good. Identify the observational units and the variable corresponding to this parameter. So the observational units, what were we observing? Well, we were observing American adults and asking them if they smoked or not. So American adults. And the variable, if P is that's the proportion who smoke. What symbol represents the population proportion 0.209? Well, that'd be a P. What does the CLT say about how this sample proportion who smoke would vary from sample to sample? Well, it says that if the samples are random and independent, and N times P is great. Oops, that should be N times P. Can't write. N times P is greater than or equal to 10, and N times 1 minus P is greater than or equal to 10. Then the shape is normal. The mean is equal to P, and the standard deviation is found by doing P times 1 minus P divided by N. Draw a sketch of this sampling distribution predicted by the CLT. So it's normal. It's going to be a bell curve. The mean is going to be 0.209. Then shade the area corresponding to a sample proportion exceeding 0.25. So 0.25 would be past that, 0.25. And so exceeding would go this way. All right. We probably need to find that standard deviation. 0.209. The opposite was 0.791 divided by the population size of 100. Got 0.04 basically. Calculate the probability that the sample proportion is greater than 0.25. Well, we know our mean, and we know our standard deviation, and we know its normal distribution. Normal distribution Now, on here, the lower boundary would be 0.25, and the upper boundary would be 1 times 10 to the 9999 power. The mean is 0.209, and the standard deviation is 0.04. Whoops. I think I put too many nines. I didn't know you could put too many nines. Oh well, I learned. It gave me 0.1527. Suppose you instead plan to take a random sample of 400 adults. Find the probability the sample proportion who smoke will exceed 0.25. So you would actually have to change the standard deviation. That's all that's going to change. The mean would stay the same, but the standard deviation would change. Whoops, I hit the wrong one. Okay. Oh, clear. Quit. Be careful if you hit the wrong one. Normal CDF, we're doing the same thing. I wish I kept mine in there instead of making a mistake. 1 times 10 to the 99th, 0.209. This standard deviation ends up being 0.02. And I got 0.49999. That does make sense. Okay, so oh, I put in the wrong thing. That's why it looked funny. This should be 0.25. Oh, goodness. I know. I was like, why is that so close to the middle? It should be 0.02. Gosh. 0.02. This means that if you sample 400 adults, only 2%, there's a 2% chance that over 25% of them say that they smoke. The probability of finding that is 2%.